property. So let's do some very easy exercise on projective modules. Recall. So we are following Weibel's book on homological algebra. An object P in a abelian category. Let's say abelian category A is called projective if it satisfies the following universal lifting property. So given any surjective map, and another map from P to C, there exists at least one map factorized through this factorize this gamma through G. Making this commutative. This is the definition part. We mostly concern with the case A is the category of R modules. Notice that free modules or free R modules are projective. Projective R modules, and also direct summand of free R modules. A projective. So let's take this as a small exercise. Just recall the definition. Yes, you have some R module and a surjective of R modules, and then you have some free R module with R linear map J and gamma. Then I claim there exists a map beta, making this commutative. Actually, just look at your basis as free R module. So suppose E1 is mapped to C1, ED is mapped to CD, because here you have a surjective map J, so you could have some previous pre-image. Let's say they're not necessarily a unique one, but just select those BI mapped to CI, and then I'm going to define my beta to map this EI to bi, and then by R linearity, this defines our linear map and making the diagram commutes, right? When it is direct summand, this still works because let's say you have direct summand. Let's say P is a direct summand of some free R module, and then given map from P to some surjective R linear maps, then it's very easy to construct this beta. Basically, how do you do is that you could factorize through RD, which is P direct sum with P prime, and so you just map your element x to x0, and then x1 map to gamma of x. This is obviously R linear, and the composition is the previous gamma. This is gamma. And so this factorize to some map beta, and then the composition, let's call it beta tilde. This makes the diagram commutes, which means that if you have direct summand of free module, then of course you construct a map on the free module, and then the free module factors tells you that you have factorization of your direct summand. Exercise 2. This is a small proposition. Actually, we want to show that projective module, not only that free modules and direct summand of free are projective, but projective implies free or direct summand of free, which means this is if and only if an R module is projective, if and only if it is a direct summand of free R module. Let's do the proof. Let's denote R A, the free R module, generated by taking all the elements of A as generating set. On the set, underlying and R module A, we see that for any R module A, I mean, there is a map, let's call it pi, from RA surjective onto A. So just take for any element, small a, then you take that factor, right? The product of R, there is 1 corresponds to, let's, without loss of general, let's suppose this corresponds to A, so it's indexed by A, and then we will map this to A, right? And then by R linearity, this gives you a surjective map of R modules. And then by the universal property of projective modules, there exists a unique, not necessarily unique, there exists some R linear map beta making this commutative. In other words, I would rather call it S, and this S compose, pi compose S gives the identity on A. This is implying that this splits, right? And this is equivalent to A is the experiment of RA. And then we prove that any projective is the experiment of our free R module. Okay, now let's exercise 3. So give some examples of projective but not free. So let's take 2 examples from Weibel's book. Firstly, consider so I'm taking R to be Z mod 6, and then notice that it is also the product, ring product of Z mod 2, Z mod 3, for example, by Chinese remainder theorem. Okay, and then let's talk about as R module. Then the 2 mentioned are projective R modules, because their direct sum as R modules in the whole space, which means it's a free R module, right? But then notice this neither of it is free armody. For example, under this ring product, you take non-zero elements of R, let's say 0, 1, then this 0, 1 as elements of R. If it's free mode, there should be no torsion, but then you notice this non-zero element kills this all the elements of this submodule of this R module. This implies this is not free module. Second example, let's take our ring R. To be all combined matrices. Over a field F. So this is a ring under Voice addition and matrix multiplication. Consider the column vector space is Fn. So and then this arc acting on this way by left multiplication. Notice that as left R module R is the direct sum with columns. Each isomorphic to this column space weight. Right, so R is actually weight n times and so in particular V is projective R module. But not free. Why? Because any free R module would consist at least what dimensional ref? At least d times n square. So let's write it this way. So RD has dimension obviously n squared times d over f, right? I mean, as a f vector space, this free R module has dimension d times n squared, while this R module V has only dimension n over f. It cannot be free. Finally, let me put a remark. The category A of finite abelian groups is an example of an abelian category that has no projective objects.